Now we turn from steady DC to alternating current, the kind that comes out of your wall socket. In this outcome, we'll explore waveforms, peak and RMS values, Ohm's law in an AC setting, power, rectification, and phase. Let's dive in. So, what actually makes alternating current different? In DC, charge flows one way only, as it does from a battery. In alternating current, the current keeps reversing direction, with the voltage rising, falling, reversing, and repeating in a steady cycle. Here in the UK, the mains supply is AC at 230 volts and 50 Hz. The big reason we use it is that transformers can change AC voltage easily, which makes it efficient to generate and to send over long distances. Mains AC traces out a smooth sine wave when you plot it against time. At any instant, the voltage is given by the peak. Voltage times the sine of the angle theta. It climbs to a positive maximum, falls back through zero, then swings negative before repeating, and one full up and down pattern is called a cycle. With time along the bottom and voltage up the side, the wave is perfectly symmetrical, so its average over a whole cycle works out to zero. Let's fix a few terms. A cycle is one complete repetition of the waveform. The amplitude is the maximum value it reaches, measured from the zero line. The instantaneous value is simply the voltage or current at one particular moment. Sinusoidal means shaped like a sine curve, the natural AC waveform, and an alternation is one half of a cycle, either the positive or the negative part. Two quantities describe how quickly the wave repeats. The period, T, is the time for one complete cycle, measured in seconds. The frequency, F, is the number of cycles completed each second, measured in Hertz, where 1 Hertz is one cycle per second. They're reciprocals of each other. Frequency equals 1 over the period, and the period equals 1 over the frequency. UK mains runs at 50 Hz, so it goes through 50 cycles every second, and a higher frequency simply means a shorter period. Let's calculate the period of UK mains, which runs at 50 Hz. The period equals 1 over the frequency, so that's 1 divided by 50, which comes to 0.02 seconds. Converting to milliseconds, we multiply by 1,000, giving 20 milliseconds per cycle. So each complete cycle of the mains takes just 20 milliseconds. There are a few different ways to quote the size of an AC signal. The peak value is the maximum it reaches in one direction. The peak-to-peak value runs all the way from the positive peak down to the negative peak. So for a sine wave, that's simply twice the peak. Then there's the RMS value, which gives the equivalent steady DC heating effect. RMS stands for root mean square, and it's worth remembering that the quoted mains figure of 230 volts is an RMS value, not the peak. Let's unpack that RMS idea a little more. Because AC is always changing, we need one effective number to describe it. And the RMS value is the DC value that would deliver the same power to a resistor. For a sine wave, the RMS voltage is the peak voltage divided by the square root of 2, and the same goes for current. Since the square root of 2 is about 1.414, the RMS value comes to roughly 0.707 times the peak. Turn that around and the peak equals the RMS value times the square root of 2. Almost every meter and rating you'll meet is quoting RMS. Let's find the peak voltage of the mains from its RMS value of 230 volts. Peak equals RMS times the square root of 2, so that's 230 times 1.414, which gives about 325 volts. The peak-to-peak value is twice that, so 2 times 325, coming to roughly 641 volts. So, although we call it a 230-volt supply, it's actually swinging up to around 325 volts each way. Let's put peak and RMS side by side. The peak value is the single highest point reached, always the larger number, and it matters when you're sizing insulation for safety, about 325 volts for the mains. The RMS value is the effective heating value, equal to the peak over the square root of 2, or about 0.707 of the peak, and it's the figure printed on meters and equipment ratings, 230 volts for the mains. Same supply, two different but related numbers. The good news is that for a purely resistive AC circuit, Ohm's law still holds: voltage equals current times resistance. The golden rule is to keep like with like, use RMS voltage with RMS current or peak with peak, but never mix the two in one calculation. And in a pure resistor, the voltage and current rise and fall exactly together, which is what we mean when we say they're in phase. Here's a quick example. A 46 ohm resistive heater element is connected across the two 30-volt RMS mains, and we want the RMS current. Using Ohm's law with RMS values, current equals voltage over resistance, so that's 230 divided by 46, which gives 5 amps, so 5 amps RMS flows through the element. Let's pause for a quick check. Can you state the relationship between the period and the frequency? Can you explain why the mains voltage is quoted as an RMS value rather than the peak? And can you convert a peak voltage of 100 volts into its RMS value? Give those a try before we carry on. Power in an AC circuit is the rate at which electrical energy turns into heat, and in a resistor that comes out as heat and sometimes light. Working with RMS values, power equals the RMS voltage times the RMS current. And just as with DC, there are two more forms: the RMS current squared times resistance, or the RMS voltage squared over resistance. The important point is that using RMS values gives you the true average power over the whole cycle, in watts. Let's find the power in that heater element. It's carrying 5 amps RMS from the 230-volt RMS supply. Power equals voltage times current, so 230 times 5, which is 1150 watts. We can check it another way with power equals current squared times resistance. 5 squared times 46 is 25 times 46, also 1150 watts. So the element dissipates about 1.15 kilowatts. Resistor networks on an AC supply behave just like they do on DC, as long as you stick to RMS values. Resistors in series carry the same current throughout, and their resistance add up, with the supply voltage dividing across them in proportion. Resistors in parallel share the same voltage across each, so you apply Ohm's law and the power formulae exactly as you would in a DC circuit. Let's work one through. Two resistors, 10 ohms and 15 ohms, are in series across a 100-volt RMS supply, and we want the current and the voltage across each. The total resistance is 10 plus 15, so 25 ohms. The current is 100 over 25, which is 4 amps. Then the voltage across the 10 ohm is 4 times 10, that's 40 volts, and across the 15 ohm, it's 4 times 15, so 60 volts, and 40 plus 60 gives back our 100 volts, so it checks out. Plenty of devices, your phone charger among them, need DC rather than AC, and the process of converting one to the other is called rectification. It relies on diodes, which allow current to flow in only one direction, conducting when forward biased and blocking when reverse biased. That blocking action is what lets us remove or redirect the reversed half of the wave, and there are two common arrangements: half-wave and full-wave rectifiers. Let's compare the two. A half-wave rectifier uses a single diode and passes only the positive half of each cycle, throwing the negative half away, so the output is bumpy and rather inefficient. A full-wave rectifier uses 4 diodes in a bridge or a center-tapped arrangement, so that both halves of the cycle are used, with the negative halves flipped up to positive. The result is a smoother and far more efficient output. Let's look a bit closer at how the diodes do it. In half-wave rectification, only half the input energy ever gets used. The full-wave bridge, with its 4 diodes, inverts the negative halves, so you end up with a series of positive-only humps. To smooth those humps towards steady DC, we add a smoothing capacitor, and that cleaned up DC then powers electronics like radios and chargers. On a circuit diagram, the diode symbol's arrow points in the direction it allows current to flow. Let's talk about phase, at least in words. Phase describes where a waveform has got to in its cycle at a given moment, and two AC waveforms can reach their peaks at different times. The phase difference is the angle by which one leads or lags the other. In a pure resistor, voltage and current are in phase, 0 degrees apart, but once you add inductors or capacitors, they fall out of step. For now, we'll treat phase only qualitatively, without any calculation. Let's collect the key terms from this section. Rectification is converting AC into DC using diodes. A diode is a component that allows current one way only. Forward bias is the condition in which a diode conducts, and reverse bias is when it blocks. Phase difference is the angle by which two waveforms are out of step, and in phase describes two waveforms that peak at the same time, 0 degrees apart. Here's a dependable method for AC problems. Read the question and list what you know, with units. Decide whether each value is peak or RMS, and convert if you need to. Pick the right formula, whether that's Ohm's law, a power formula, or the period equals 1 over the frequency. Substitute carefully, keeping your units consistent, then calculate and check the answer is a sensible size, before stating it clearly with the correct unit. Let's bring it together with one problem. A 60-ohm resistive appliance runs from a 240-volt RMS supply, and we want the RMS current, the peak current, and the power. The RMS current is 240 over 60, which is 4 amps. The peak current is that times the square root of 2, so 4 times 1.414, about 5.66 amps, and the power is voltage times current, 240 times 4, giving 960 watts. Another quick check for you. Can you explain the difference between half-wave and full-wave rectification? If a 20-ohm resistor carries 3 amps RMS, what's the power dissipated? And what's the phase relationship between voltage and current in a resistor? Have a think before moving on. Before we finish, it's worth seeing where all this matters. The national grid distributes power as high-voltage AC, with transformers stepping the voltage up for transmission and back down for use. Every mains appliance is designed around that 230-volt, 50 Hz supply, and chargers and power supplies rectify it to DC for their electronics. Getting comfortable with RMS values keeps your power calculations honest, and these same principles underpin all electrical installation and design.